summit of Mount Etna collapses, and a huge pyroclastic flow threatens the settlements below. On June 2nd, Sicily witnessed a spectacular yet deeply concerning display of nature's power as Mount Etna unleashed one of its most violent eruptions in recent months. At 0924 UTC, thermal cameras at the INGV Etna Observatory recorded an event that shook not only the ground, but also our understanding of Europe's tallest volcano, the formation of a devastating pyroclastic flow. Impressive images and video footage. Don't believe us? Well, try following us. The phenomenon, described by experts as probably produced by a collapse of material from the northern flank of the southeast crater, represented the climax of eruptive activity that began in the early morning hours. Fortunately, the incandescent material did not cross the rim of the Valle del Leone, stopping after just a few kilometers without posing any danger to the population. However, videos from that day show tourists fleeing before the majestic column of ash and gas several kilometers high, tangible testimony to the power unleashed by the Sicilian giant. What makes this event particularly significant is how it connects to broader questions about Mediterranean geology and seismic activity. Standing at 3,357 meters tall, Mount Etna isn't just Europe's tallest active volcano, but represents one of the world's most complex and studied volcanic systems. Located on Sicily's eastern coast, this geological colossus owes its existence to the particular position where the African plate subducts beneath the Eurasian plate, generating intense magmatic activity. The volcano's history stretches back into the mists of time. The first documented eruptions date back over 500,000 years, and since then, Etna has shaped not only the Sicilian landscape, but also the culture and lives of local populations. The ancient Greeks called it Etna, and considered it the dwelling of Hephaestus, the god of fire, while for the Romans, it was where Vulcan forged the weapons of the gods. From a scientific perspective, Etna is classified as a stratovolcano, characterized by a cone built from alternating lava flows and pyroclastic deposits. Its complex structure includes four main craters: the central crater, or voragine, the northeast crater, the southeast crater, and the new mouth. Each presents specific eruptive characteristics and contributes to the volcano's continuous morphological evolution. What makes Etna particularly fascinating, from a volcanological standpoint, is its almost constant activity. Unlike other volcanoes that can remain dormant for centuries, Etna presents regular eruptive manifestations ranging from tranquil lava effusions to spectacular lava fountains, up to the most violent paroxysmal episodes like the one on June 2nd. But here's where things get really interesting. In recent decades, Etna has been undergoing a profound transformation that simultaneously fascinates and concerns the international scientific community. The volcano, traditionally characterized by predominantly effusive activity with fluid lava flows that were relatively predictable, is showing increasingly explosive behavior with frequent paroxysms and pyroclastic flow production. The numbers tell a striking story. According to volcanologist Boris Benker, until the 1970s, Etna produced paroxysmal events at a frequency of 1 to 3 every 10 years. Starting from 2000, this frequency increased dramatically, reaching dozens of episodes per year. 2021 represented a record year, with about 60 paroxysms recorded, characterized by intense pyroclastic material emissions that significantly modified the volcano's summit profile. This evolution is particularly evident in the Vorogene crater, which has transformed from a depression into a cone due to pyroclastic material accumulation. Scientific research suggests that Etna's magma over the last 60,000 years has been approaching in composition that of Pacific Ring of Fire volcanoes, notoriously characterized by explosive activity. The most credible hypothesis to explain this change involves a possible laceration of the Earth's crust that would have allowed migration of magma, richer in gas and silica, from the Aeolian regions toward Etna. This new type of magma, characterized by greater viscosity and gas content, favors explosive fragmentation, generating eruptive clouds and increasingly frequent pyroclastic flows. And speaking of pyroclastic flows, the pyroclastic flow that occurred on June 2nd represents one of the most fearsome and spectacular volcanic phenomena in nature. The U.S. Geological Survey doesn't mince words in describing their danger. If you witness a pyroclastic flow, run in the opposite direction as fast as possible. But what exactly are these phenomena that inspire such fear? A pyroclastic flow is a high-density mixture composed of ash, volcanic gases, pumice, rocks, and incandescent lava blocks. This violent cocktail of materials has the ability to destroy everything in its path, moving down volcano slopes at speeds that can exceed 200 kilometers per hour. The danger lies primarily in two factors: extreme temperatures, which can reach 1,000 degrees Celsius, typically between 200 and 700 degrees Celsius, and propagation speed. Even the slowest pyroclastic flows exceed 80 kilometers per hour, making escape practically impossible for anyone in their trajectory. Volcanic history is littered with tragedies caused by these phenomena. The pyroclastic flows from Vesuvius in the 79 AD eruption traveled at 200 kilometers per hour with temperatures of 400 degrees Celsius, forever sealing the fate of Pompeii and Herculaneum's inhabitants. More recently, the Mount Pelée eruption of May 8, 1902, generated a pyroclastic flow that killed about 30,000 people in Martinique, practically destroying the city of Saint-Pierre. If you enjoyed this video, don't forget to hit the like button and subscribe for more amazing content. Pyroclastic flows form primarily in two ways: by collapse of the eruptive column, when volcanic material loses the ability to rise due to cooling and increased density, or during lateral explosive eruptions, where rock, lava, ash, and gas head directly toward the volcanic cone's slopes. The latter would be the case for the June 2nd event on Etna. Exposure to this incandescent material has catastrophic effects on the human body, as studies on victims of the Vesuvian eruption testify. The released material is also highly toxic and can pose health dangers even after the hot phenomenon ends, accumulating to impressive heights and giving rise to landslide events and lahars. This brings us to the new challenges facing one of Italy's most densely populated regions. The behavioral change of Etna involves new challenges for volcanic risk management in one of Italy's most densely populated regions. Although recent pyroclastic flows have been limited to uninhabited areas like Valle del Bove or Valle del Leone, their increasing frequency statistically increases the probability of events that could reach populated zones. Volcanic ash already represents a concrete problem for the Sicilian population. Often carried by winds, it causes considerable inconvenience, such as temporary closure of Catania Airport, road traffic problems, and public health impacts. Studies conducted in Catania have detected an increased risk of thyroid cancer, linked to groundwater contamination by heavy metals of volcanic origin, highlighting additional long-term environmental and health impacts. Constant surveillance by the INGV Etna Observatory, with its thermal cameras and seismograph network, remains fundamental for monitoring activity and predicting critical events. However, safety also depends on risk awareness by residents and visitors, who must strictly avoid dangerous areas during intense activity phases. This is particularly crucial as we consider what happened just days later in another part of the Mediterranean. While Etna was calming after the June 2nd eruption, a few hundred kilometers away, in the early hours of June 3rd, another geological phenomenon shook the eastern Mediterranean. A violent magnitude 5.8 earthquake struck a sea area between the island of Rhodes, Greece, and southwestern Turkey at 2:17 local time. The quake, with a hypocenter at 68 kilometers depth, caused 69 injuries in Muğla, Turkey, mainly due to panic triggered by the tremors. Tragically, a 14-year-old girl lost her life following a panic attack. On the island of Rhodes, despite the earthquake being felt intensely, no injuries were recorded. From a geological perspective, the affected area represents one of the most seismically active zones in the Mediterranean. Here occurs the subduction of the African plate beneath the Eurasian plate, a process that originates numerous fault systems, particularly affecting the entire Dodecanese area. The seismic map of the region clearly shows the frequency of historical earthquakes. Each circle represents a past seismic event, with sizes proportional to magnitude. Greek seismologist Efthymios Lekas reassured the population, stating that the event will not have a significant impact on the surface, there will be no tsunami, and above all, there will be no rich sequence of aftershocks. But this raises a fascinating question that has always intrigued geologists and volcanologists. The temporal coincidence between Etna's June 2nd eruption and the Aegean earthquake of June 4th to 5th raises a fascinating question that has always intrigued geologists and volcanologists. Are these phenomena truly distinct, or does the Mediterranean lie above an enormous and capillary geologically active region where volcanic eruptions and earthquakes are interconnected? The answer isn't simple and requires analysis of the Mediterranean basin's complex geological structure. The Mediterranean is indeed the result of millions of years of tectonic plate interactions, with the African plate moving northward, colliding and sliding beneath the Eurasian plate. This process, known as subduction, generates a series of interconnected geological phenomena manifesting along the entire arc from southern Spain through Italy to Greece and Anatolia. Italy finds itself in a particularly delicate position within this system, being crossed by the contact line between the two main plates. This position explains why the Italian peninsula is characterized by intense seismic activity along the Apennines and important volcanic systems like Etna, Vesuvius, Campi Flegrei, and Stromboli. Etna, in particular, occupies a unique position in this geodynamic context. The volcano is located in the transition zone between the compressive front of the Apennine chain and the extensional system characterizing eastern Sicily. Love content like this? Give it a thumbs up, drop a comment, and be sure to subscribe. This particular position could explain its intense activity and recent behavioral transformations. Regarding connections between distant phenomena, the scientific community still maintains cautious positions. While it's undeniable that the entire Mediterranean basin is characterized by common geological dynamics, demonstrating direct connections between specific events like Etna's eruption and the Rhodes earthquake requires much more in-depth analysis. However, some clues suggest possible regional-scale interconnections. Tectonic stress systems affecting the central and eastern Mediterranean can influence each other reciprocally, creating chains of events that propagate through the Earth's crust. Recent studies have highlighted how large earthquakes can trigger volcanic activity at considerable distances, and vice versa. What we're seeing might be just the latest chapter in this ongoing geological story. The increasing geological activity of the Mediterranean makes the development of integrated monitoring systems and internationally coordinated prevention strategies increasingly crucial. Italy, with its network of volcanological and seismological observatories, represents a world excellence in this field. But the transnational nature of geological phenomena requires ever closer cooperation with neighboring countries. The INGV Etna Observatory continues to perfect its surveillance systems using cutting-edge technologies like thermal cameras, high-sensitivity seismic sensors, volcanic gas analyzers, and satellite systems for ground deformation monitoring. These instruments allow real-time monitoring of volcanic activity evolution and provide timely alerts to the population. Simultaneously, scientific research focuses on understanding the mechanisms governing Etna's volcanic activity evolution. Study of magma geochemical variations, analysis of precursor seismic patterns, and modeling of volcano internal processes represent the frontiers of modern volcanology. The main challenge remains translating scientific knowledge into effective risk communication and civil protection strategies. The experience of June 2nd, with tourists fleeing before the pyroclastic flow, underscores the importance of correct information about behaviors to maintain during intense volcanic activity. As we look toward the future, one thing becomes increasingly clear. We're witnessing the Mediterranean in a state of geological awakening. Whether it's Etna's explosive transformation, increasing seismic activity in the Aegean, or the ongoing unrest at Campi Flegrei, the signs point to a region where the Earth's internal forces are particularly active. This doesn't necessarily mean we're heading toward catastrophe, but it does mean we need to be prepared. The key lies in understanding these processes, monitoring them carefully, and developing resilient communities that can coexist with geological risk. As Etna continues to reshape itself and the Mediterranean seabed continues to shift, we're reminded that we live on a dynamic planet where change is the only constant. The June 2nd eruption of Mount Etna represents much more than a simple volcanic event. It's the tangible manifestation of a geologically alive and continuously evolving planet. The volcano's increasingly explosive behavior, together with persistent seismic activity in the eastern Mediterranean, reminds us that we live on a dynamic Earth where internal processes continue to shape the surface and influence human life. Etna's transformation from gentle giant to potentially more dangerous volcano requires adaptation of volcanic risk coexistence strategies. It's not about fueling alarmism, but developing a conscious and scientifically founded risk culture. The Mediterranean, with its complex network of faults, volcanoes, and active tectonic systems, will continue to be the theater of spectacular and sometimes dangerous geological phenomena. The key to safe coexistence with these phenomena lies in combining advanced scientific research, increasingly sophisticated monitoring systems, and an informed and prepared population. While scientists continue to question possible connections between the various geological phenomena of the Mediterranean basin, one thing appears certain: vigilance and preparation remain our best allies for facing the challenges posed by a geologically active planet. Etna, with its majestic presence and growing restlessness, will continue to be one of the most important natural laboratories for understanding the secrets hidden in the Earth's depths. If you found this video insightful, don't forget to like, subscribe, and share it with your friends. See you in the next episode.